a quantitative study of 1D motion, okay? So remember, we only studied two kinds of motions. Yes, one is a constant velocity motion. There's nothing to do at all, okay? Constant velocity motion, it's so easy. All right, now constant velocity motion in 1D means it has a constant speed. So don't think that now 2D you cannot have constant velocity. So otherwise, now what does constant velocity? Let me further emphasize here, meaning it has a constant direction. So directional motion never change. All right, let me kind of emphasize here, because sometimes people just superficially read the phrase, then they begin to ignore certain understanding. Okay. So a constant velocity motion is a very strict motion. Otherwise, its direction never change. Do you think so? All right? Because constant velocity requires, because the velocity has direction meaning and a magnitude meaning, so that it means your direction cannot change. If you change the direction, it's not a constant velocity motion. Okay? And it's a speed. Its instantaneous speed never change. Never change. Or otherwise, a constant velocity motion is a constant speed, constant direction motion. Yes, it's a constant speed motion. Constant speed motion in a fixed direction. Make sense? You will say, wow, that's easy. Okay, that's easy. All right, and because you guys are learning even in middle school in some math problems about those speed of motion, constant, those speed versus distance. So otherwise, a constant velocity motion can be fully solved, based on what you learned before. Okay, so if you're ever confused by constant velocity motion, sometimes you can just how do I say that? Just visualize it. Okay, by visualization, you will never get it wrong. For example, I can have a vehicle moving because I have to go along certain specific direction. You cannot have a constant velocity motion, not a 1D motion. Okay? So constant velocity motion must also be a one-dimensional motion. Do you agree? I hope you agree. All right? Okay. So it has to be 1D. Now suppose I have this 2 meters per second. All right, and now suppose this at the t equal to 0. Now I keep it moving. So the only problem you can ever have would be, say now after t equal to 5, now where I am. You will say, oh, that's such an easy problem. Yes, all right. So at the t equal to 5, if I want to find my displacement, now in the meantime, if they tell you now, knowing, right, this constant velocity is the velocity equal to 2 meters per second. Now, if they already tell you velocity and it's already showed you this number is a positive, so that also means this is your positive direction. You have no choice. Okay, so don't struggle with yourself. Says, oh, should I define velocity, the direction, all that? Okay, because oftentimes there are those underlying kind of like understandings already. Right? If they tell you velocity with a positive number, basically all they tell you the positive direction is already kind of not stated but defined. Okay? All right? So just kind of use your common sense. Just label your positive direction. If you want to label those type of like past representations, you can do that. Okay? And then you will say, oh, this again, I'll find the D in 5 seconds. You will say, oh, that's so easy now. Right? So D would be equal to velocity times time duration, yes? Time t. Because the definition is v equal to d over d, so you end up with 2 times phi equal to 10. Now, but what if, all right, saying that some people say now, if my velocity is negative, can I also do that? Yes, I can. Say knowing, so don't be scared by that, okay? Velocity, now maybe they will not say that. They will say, hey, knowing knowing the vehicle, the car, is moving with a speed, a constant speed of 2 meters per second to the left. You see? Or sometimes they say to the west. Okay, now find d in 5 seconds. Now here I also say find its displacement in 5 seconds. Okay, now here, so this is 1, and this is b. Now for b, be careful, okay? Because in this kind of case, you have to show the representation. If you do not show the representation, people can easily give you the wrong answer. Oh, they show the representation, but suppose they didn't define anything, then also be careful, okay? So say this now, I will label like this now, yes? 2 meters per second, okay? And now here depends on how you define positive. Now suppose I still define the positive like this. What would be my answer? Now my answer would be, all right, now since, right, it's a constant velocity, right? Since d equal to v times t, but remember displacement has direction and magnitude information, right? My formula representation is still the same, okay? Because that's coming from the definition. Now here, be careful, be negative 2 times phi, and it's negative 10 meters. Now, should I be confused or should I be scared by negative 10? No, not at all. Because I do know that this is at t equal to 0, yes? This is my 0 reference here. I do know after 5 seconds, I'm supposed to on the left side. Okay, let me kind of show you here why this negative makes sense. Because I do see some people don't want to use this type of past representation, then they are scared about what they get. And I do know the distance here, would it be my distance equal to 10 meters, no problem. Yes? But how do I define displacement? You will say, oh, displacement is defined by from the initial place to the final place. Do you remember our definition? Yes. See? I'm supposed to define displacement like this. It has an arrow. See? This is a displacement. My black line representing my displacement. Is this arrow opposite to my positive direction? You will say yes. That's why it must be negative. You see? My magnitude is 10 and my direction is opposite to the positive. So don't be scared by those negative and the positive signs. All right? If you link with what you get with those definitions, everything makes sense. All right? So that's why the system we develop here is very, very precise. Okay? Right? Because you're supposed to carry such direction information, such magnitude information. Okay? If you instead just for the sake of cleverness says, oh, should it be positive 10? Turns out their answer is wrong because they are asking you for displacement. Okay? So that's why your answer must be combined with such a kind of representation, graphic representation. If you do not show such kind of graphic representation, your answers are meaningless. Okay? Your answer is meaningless. Make sure, right? But oftentimes we do not do that, right? Because here I'm intentionally set the positive direction toward the right because that's the usual way we do it. All right, but you are not supposed to say, "Oh, that's the only way. That will be the forever way. That will be the way that my teacher will understand." No, you have to show it. Okay, keep that in mind. Okay. All right, so constant velocity motion, there's not much you can do about it. The only thing you can do, make a thing a little bit complicated, would it be, see, I can have two sequential constant acceleration motions. All right, so for example, right. But again, it's not difficult anymore, yes? All right, so if you plot it, so it's like a here, then I have another like a here, something like this, okay? So this is a V, this is a T. Now overall, it's not a constant velocity motion. Why? Because here I have magnitude equal to 10. Now here I have magnitude negative 5. So overall, it's not a constant velocity motion, but in each segment, up to say this, like say 5 seconds, all right, this is a 10 seconds. All right, in each segment, I have a constant velocity motion. So I can sequentially do it. For example, in this case, since the plot, this positive direction is already defined. So here you see it's already defined. You just based on such plot direct to the calculation. You do not need to show this anymore, right? Because here I don't have a plot, so I have to show it, right, for people to understand. So here some people already give you the plot, means underlying direction is positive direction already defined. You don't care about your underlying actual direction. You just need to know, oh, it's underlying positive direction defined because you give me a positive velocity. See, this is a velocity, right? You give me negative velocity, okay? So otherwise, then you just stick to it. So for the first, right, from t equal to 0 to t equal to 5, how do I do d? D equal to what? D equal to, what's my displacement? V times t, yes? Equal to 50. All right, now again, I can do the next one. Now from t equal to 5 to t equal to 10. Now again, my formula is still the same. My v equal to what? Negative 5. My time duration again is 5, so it's negative 25. See? All right, so the overall displacement right, d, let's call this d1, d2, right, will be equal to d1 plus d2. Turns out equal to 25 meters. All right, does that make sense? I'm sure it makes sense, because if I imagine it in the actual motion, all right, my vehicle starts from this place. Now in the first 5 seconds, I will travel up to here. All right, for 5 seconds, I traveled 50 meters. Now in the next 5 seconds, I went backwards. Yes, in the next 5 seconds, I went backwards. By how much? 25. Now what's my final displacement? Final displacement is from initial place to the final place. See, this is my d. Now this is my positive direction. See? All right? Is my final displacement indeed equal to 25? Positive 25? Yes. Makes sense. You see? Okay? So once you precisely stick to the recipes, okay? And don't try to be inventive. Don't try to take shortcuts. All right? Don't try to kind of like do it based on your old understanding about those distance. You will be perfectly fine. All right? You will never make a mistake. Okay? But anytime you deviate from that, you can easily make a mistake. Okay? Because the direction thing is not naturally built into our conversation or our usual type of like understanding. Okay? Now, so the constant velocity motions are very simple. Now, next one, it's called a constant acceleration motion. All right, now I would do it based on the plot. Okay, so that you can link those formulas, because you will have two ways of doing those type of motion problems. One is graphically, see, you can do it graphically. Or another way would be based on the certain formulas, okay? So I would develop this formula based on the plot. Then you can easily understand how the thing would work. I'll give you several different cases, okay? So the easy type will be this type, V and T. Now my V starts with 0. Because I told you before, yes, constant acceleration motion is represented by a straight line in the VT plot, okay, in the VT plot. So in such kind of in the VT plot, remember, let me say, how do I say this thing? First, the slope of this, slope of the line in the VT plot is the acceleration. Remember that. Certainly you already know that. Yes? All right, now how can this become useful for me? So for this particular case, suppose I start from t equal to 0, okay? Now at t equal to 0, my v equal to 0. Make sense? Yes? Now suppose I want to find out at t equal to t1. Suppose this is t1. What is v1? What is v1? You will say, wow, that's such silly question. Yes, so easy. Yes, I know the slope. Slope is defined by v1 divided by t1, and certainly v1 equal to acceleration times t1. Make sense? That's so easy. Okay? All right? For this particular case, I'll give you several cases. Those are all special cases, right? This is acceleration, so I call it A. Okay, the slope of the line is the acceleration. Okay, and the slope is defined by, say, the height divided by the base. Yes? All right? So that way I can find my velocity at any time. Right? O in general, so I have a general question, a general formula now. O in general with V0, V at t equal to 0 equal to 0. Now V at any time is always equal to A times time. Okay? A times time. All right? Very simple. But that's not enough yet. We also want to figure out what is the displacement. Okay? So this is the first thing. Second, you need to remember, we already introduced before, the area under the line in VT plot is the displacement. Okay, we define this based on the constant velocity ones. Remember somewhere here? Yes, it's area representing displacement. Yes, but we can visualize. Don't you think I can visualize a slope can be made of lots of constant velocity rectangles? Yes, all right? All right, so in the end, that concept still is true. So area underneath the VT line, or otherwise this triangle will representing displacement. Let me mark this as well. Now from this, can I easily define my displacement now? Yes, I can. Right, so this D1, would it be equal to the area of the triangle? Yes, 1 over 2 times the base times the height. What's my height? Is V1, yes? But the V1, I already have it. It's A times T1. So I get my formula, half a t1 squared. So the displacement equal to half a t1 squared. Now in the future you will go memorize it, okay? But for now, sometimes if you are confused of how to solve, you just draw the plot. And from plot you can get everything you want, okay? So that's the first case. Now sometimes you will say, what if my accelerations go the other way? So I give you several cases, okay? Overall, I probably give you 4 cases. That'll be, you will be able to fully understand those formula. Now B, okay, what if my acceleration is negative, but it still starts from 0, okay? Vt, and I still start from 0. Okay? So this times a is negative, right? So the slope is negative. So a is negative. Make sense? All right. Now, can I still find out what's my velocity at the t1? Right? Yes, I can. Suppose this is v1. Right? Then v1, you will say, hey, I still can based on my slope things, right? So if I treat this slope as a positive, then I can say, oh, it's a v1 over t1 equal to that slope. But since it's negative, my formula never changed because a times t1. Now, since a is smaller than 0, so v1 is smaller than 0. You will say, oh, that makes sense. All right? Because you are kind of like, at least based on plot, you see my v1 is increasing over time, but it's in the negative direction. Indeed, it should be negative. Now here, should I try to put a negative over there? I don't, because as long as I'm aware, I have to plug in a negative value for a, because I know this a must be negative. All right, then we'll be fine. Now, can I do the same thing here? The displacement. In t1 time. You will say, oh, that's easy too, because it told me the area covered below it is displacement. Now this area is below my x-axis, below my t-axis. So this area is supposed to be negative. But should I struggle with this negative sign? I don't. All right. Now turns out the d1 is still the same formula. Do you begin to see the magic? All right, because that's the thing that sometimes people make mistake about. Now this one's still smaller than 0, as long as you plug a with a negative sign. All right, okay? So again, this part is easy, okay? So we already have 2 formulas that pretty much repeat each other, but you have to understand, when you're solving a real problem, I must take care of the sign. If you don't take care of the sign, you will end up with those wrong values, okay? And this wrong value can carry over, suppose, to the next case. What if my starting point is not a 0? Now again, I have a constant acceleration motion, because constant acceleration motion is always represented by a straight line. All right, it does not depend on where you start, okay? Now this time I have the starting velocity. This is at time t is equal to 0, yes? Now suppose, again, the slope is a. Now this time a is larger than 0 because it's positive slope, okay? Now suppose this time I want to find out what is the velocity at the t1. Then you'll say, oh, wait a minute. This one should be here now, so this is the v1. Oh, the slope. Now I need to do it based on this kind of things. I need to subtract this v0. Otherwise, v1 minus v0 should be equal to the slope times t1. Oh, t1 minus 0, yes? t1 minus 0. Oh, now I find a new formula. So this tells me if my starting velocity not a 0, I should have a v0 plus a t1. That's a formula. And don't you think this kind of looks like a more general now? Yes? I don't care about the starting velocity as long as you tell me what. Right? Could it be positive? Could it be negative? I don't care. The formula is the same as long as I take care of the sign. Okay. Now in the meantime, displacement. How about displacement d1? Oh, displacement is still its area underneath it. Now in this time the area consists of two parts. I have a rectangular part and I have a triangular part. So let's take care of the rectangular part first. The rectangular part would be v0 times t1. Now plus the triangular part. The triangular part is 1 over 2, all right, times the base times the height. Height is v1 minus v0. Okay, now I put them together. v1 minus v0 is at1, so I have another formula. It's a v0 t1 plus half a t1 squared. You will say, wow, we are beginning to get those more general equations, yes, general formulas, because this one turns out also work if my acceleration is a negative. Can it work like this? I'm sure it can. All right, this time intrinsically my a is smaller than 0. Now again, suppose I want to find out everything related to t1, right, from 0 to this v0. Remember, this v0 is also negative now. This v0, in this case, smaller than 0. Yes? All right, now you will find out exactly the same thing. I can still find out my v1. Right, v1 will be here. Yes, this will be v1. v1 will still be v0 plus at. Now, should I be worried about my number may not match? No, it will match. Because why? Because v0 is smaller than 0. A is smaller than 0. See? I add them together. Indeed, I get a bigger magnitude value of v1, except it's more negative. Nothing wrong with it. But the formula-wise, it's exactly the same, you see? Same thing with the d1. Again, I have this rectangle, but this rectangle will be negative value now. v0 t1. Now this is negative, yes? Now plus half. Now again, do the same thing. You will find out a t1 squared. Now again, this one's negative. Again, nothing wrong with it. Okay? As long as you take care of the sign. So the sign is very, very important when you try to use this formula to calculate the problems. Now, some people say, are you sure this will also work for this? Because only one more choice will be this one. And this one looks a little bit scary, but turns out same thing. What if I have this? Are you sure this one will still work? Let's see now. This time v0 is a positive. Alright, now suppose I still want to try to find out at the t1. Now this will be v1. Let's see if I still use the same formula, would that make sense, okay? So now v1 equal to v0 plus at1, okay? Now let's analyze it. Now v0 is larger than 0. Now a is smaller than 0, right? This time a is smaller than 0. Now what does this a times t1 give to you? A times t1 give you this whole thing, the whole height. See, a times t1, I don't want to label it, okay? All right. Oh, you can say a times t1 would give you what? Would give you what? Will give you v1 minus v0. Do you agree? All right, we'll give you v1 minus v0. Or otherwise, this will give you this thing anyway, see? If you analyze the graph. Okay, so this also tells you now, I don't want to analyze this. This will also tell you, this d1, don't be scared by this. You will still get the same thing. You will still can use the same formula. Okay, or otherwise now, this is v0 t1. Now v0 t1, you have positive areas. Okay, but now this whole thing is negative, so this whole big negative area. All right, now I need whole big negative area, and then I will subtract out this v0 minus t1 basically. So it will still give you the same result. Okay, because I have the positive displacement here, negative displacement. So it's a very not easy to exact, but you can do some geometry analysis. You'll find out exactly the same. Okay. So overall, so remember this now. Formula-wise, I have two very important basic formula. Two basic constant acceleration motion formula. And this only works for constant acceleration motion, okay, in one dimension, okay, in 1D. Now here I don't, but actually it will work for two dimensions as well. So first you remember this, V final velocity will be equal to V0 plus AT. Make sure you take care of sign, or otherwise I will treat this as vectors. Okay? If the vector reminds you, when you put a number, you must take care of the sign. Another formula, the displacement in time duration t would be equal to V0 times t plus half AT squared. Now again, make sure take care of the sign. Take care of the sign. Take care of the sign. Alright, so those are the two basic ones. Now you have two more called the derived ones. Two derived formulas for constant acceleration motion. Now this too, it's mostly related to this D. For example, here I can try to replace A by those. Right? So now D equal to V0t plus half. Now I will replace this A. Now A is equal to V minus V0 divided by T. Yes? Times T squared. Now if you simplify this, it's a half-half. Now you end up with 1 over 2. All right? This time you have V plus V0 times T. Okay? All right? So it depends on what kind of parameters available, you may choose which formula to use. Okay? Which formula to use. Now I can have another one. Now another one would be a little bit tricky here. So I will use this one. Now this one tells me V plus V0 is equal to 2D divided by T. Do you agree? Yes? Now I can also use this formula. V minus V0 equal to A times T. Alright, so now I put together, I'll multiply each side, I find out. Now once you have the velocity like multiplied together same direction, you can just replace by speed. So V minus V0 square equal to, now TT cancel out, 2 times A times D. Alright, so this is my first equation. Second equation. All problem, if you don't bother to use other equation, you can always use these two equations to solve every constant acceleration motion problem. Okay? But if you're by chance, you also remember this equation, sometimes it will help you to solve problem a little bit more quickly. Okay? It's not essential, right? Because the other two are just derived equations.